In the previous video, I gave a visual demonstration of the k-means algorithm. In this video, I'll show you how k-means is implemented in Python. I'll start by importing pandas so I can easily work with my dataset. I'll also import sklearn so I can retrieve the iris dataset and instantiate the pre-written k-means algorithm. Finally, I'll import matplotlib to make a simple graph. In the second cell, I read in a public dataset, which I named EF. I also rename the columns. This is a printout of the first 5 rows. You can see there are 4 columns: sepal length, sepal width, petal length, and petal width. You are probably aware that the iris dataset actually contains class labels and is most often used for classification problems. However, I am choosing to discard the class label for the sake of this tutorial and cluster the dataset instead. It is very important when using k-means to scale your data. This is because large variations in scale between features will cause the larger features to dominate the distance calculation. Said another way, columns with large values will be treated as more important, which is not what we want. Scaling the data will help keep all features equally as important. This cell finds the average and standard deviation of each column so that we can convert the raw numbers into standard deviations from the mean. Now you can see the values have been transformed. Since our dataset has been preprocessed, we can now run k-means. The first line of this cell is calling the k-means class and telling it how many clusters we would like to have created, which I've set to 3. I chose this number because I know the dataset contains 3 labels. However, in real life, you will have to take a more mathematical approach to determine the number of clusters you will need for the problem you are tackling. I'll show you how to go about doing that in a minute. As for the second line of the cell, I am telling my instantiated k-means class to fit itself on the data and predict which cluster each row should belong to. Using bracket notation, I create a new column in the data frame called cluster. Now you can see each row of the data frame has been assigned to a cluster. If I run a value count on that column, I can see 52 rows have been assigned to cluster 2, 50 rows have been assigned to cluster 1, and 48 rows have been assigned to cluster 0. We have completed clustering. However, we have not taken a realistic approach to determining what the appropriate number of clusters should be. So I'll take you through the most common way of doing this, called the elbow method. In this code block, I want to see at different numbers of clusters how the error changes. The way I'm defining error in this case is the average distance a data point is away from its centroid. I can find this by calling the built-in attribute .inertia_ on the k-means model. What I've written here is a loop that runs from 1 to 10, each time creating k-means with a different number of clusters and returning the error corresponding to that number of clusters. I've written the results to a data frame. I'll plot this data frame for a more visual representation. What we see is that each increasing number of clusters, the error goes down. This is expected and should be the case. However, we don't necessarily want the number of clusters with the least error. I'll explain why. If we have 100 data points, we could theoretically create 100 clusters and have each cluster contain 1 data point. In this case, the error would be 0 because the cluster center, aka the centroid, would sit on top of the 1 data point in its cluster, measuring to a distance of 0. However, each data point is in its own cluster and thus nothing is grouped together. This essentially means we're back where we started. We can't say which points are similar because everyone is in their own group. This is why we plot the error. We want to see at which number of clusters the error begins to flatten. In this case, you can see it flattens at 3. There's a steep drop in the error until the 3rd cluster, in which case the error levels off. Thus, the ideal number of clusters should be set to 3. It is not the most scientific method, and that is one of the drawbacks of using k-means. However, k-means is still a widely used and very useful algorithm. Now you know how to not only run k-means, but tune the one significant parameter